Welcome to Earth Science. What's happening, everybody? So the test is tomorrow. Let's run through things that are going to be on there. Some things will definitely be there. I'll try to be specific there. The universe was formed, and you should be filling this out as you go if you didn't do it yesterday or checking your work yesterday. Uh, figure it out. Big Bang, evidence for this, and the Regents loves these simple questions. You're going to see it on the practice sheet. You're going to see it on the test. All you really got to be able to do is recognize it. The first idea was Redshift, which showed us that we have an expanding universe. It's a Doppler shift of light. That whole thing we did with Doppler effect, where you hear a car drive by and you hear the pitch change. This is the same concept, only you're seeing the wavelength of light change towards the red, indicating that the universe is expanding, everything is moving away from us. And that was pretty good evidence of the Big Bang, but it wasn't until cosmic background radiation was discovered that we really said we live in a Big Bang universe. That's it. That's and the physics of it is pretty complicated. It's like the leftover radiation from the Big Bang. That's awfully simplified, but you don't really have to get there. All you really got to be able to do is spot that as evidence of the Big Bang. So link those three in your head. You'll see one or two questions, I promise. Stars form from conjecting nebula. That's really the singular form, but that's okay. Cloud of interstellar gas and dust that comes together thanks to the force of gravity. Let's see if I can open up a website here. There's a pretty cool little function that shows that. But we'll keep going. So once there's enough kind of density within this nebula, it starts to pull it together towards the middle, will form a star. You know what I didn't put on the sheet that's going to be important, so add it. Stars powered by fusion. That'll be there as well. That'll be on the practice sheet. So once it gets dense enough, and in the middle where it's the sun's very large relative to the planets, most stars are pretty large compared to the planets, where it starts to fuse together elements, and that nuclear reaction releases a lot of energy. So this is kind of like the gravity website you guys all played with. Let me get this thing out of the way. Where if it lets you put a whole bunch of stuff out all at once, and it just programs it with the same physics, with mass and distance being what controls gravity. So gravity starts to pull things in towards the middle, everything else spins around it, and those bits begin to collide with each other. And through some chaos, this early solar system would have been very chaotic. Eventually, many solar systems form, planets going in orbits around the star. Try it one more time because it's kind of cool looking. Okay. So that's just a simple little physics toy. That's not like this isn't live video of a solar system forming, but that's the idea. If there is this cloud of all of this stuff floating around, eventually that stuff, because it's gravitationally attracted to each other, starts to coalesce, get bigger and bigger, which gives it more of a force of gravity, which makes more stuff come in, which makes it bigger, and eventually you can form. Once you let this thing run for, in our case, billions of years, you end up with a pretty stable set of planets and a bunch of stars and some random guys still flying around like Halley's Comet. So that's that. Let's keep it moving. The chunks of rock are frozen gases that form in orbit around the stars. Those will be the planets as this whole thing is coming together. All right, stars are organized according to this table. You're going to need that table for the test, no doubt. I'm feeling pretty confident. People were doing pretty good on that. So luminosity, temp are the big ones, color, size. And then some people did what is their group? That's kind of implied by the other ones, but hey, if that's what you want to say, that's okay. And in terms of using that thing mechanically, again, I think people were doing pretty good with it. Just lining up temperatures and luminosities. You will be okay. Planet's orbits have what shape? It is an ellipse. And if the eccentricity is the measure of how eccentric an ellipse is. Now, you're not going to actually have to measure it because you're on computer screens with rulers, but there might be some questions on the concepts. low eccentricities, closer to zero, the shape is more circular, which would mean less eccentric. If the eccentricity gets closer to 1, it's going to be more eccentric. It'll be more like, where's my camera? We go from a circle down to like way like an oval. That's what comets' orbits tend to be like. That's why some of the comets, I don't know if you guys saw the comet of the summer, Neowise, but it only comes once every blah, 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 hundreds of years, thousands of years, whatever it might be, because it goes shooting by us and then does this way long trip out and way long trip and then comes popping back around the sun again. Highly eccentric elliptical orbits. All the planets have elliptical orbits, though they're all pretty low. You can look at this chart here, eccentricity. They're all reasonably low. Mercury's the highest, I think. Yep. Which means that the orbits are pretty darn circular. They're pretty close to perfect circles. What else? Perihelion. Remember, A for away is the way that I still do it. I've always done it. So if you're further away, you have a low speed. You have the lowest force of gravity. Perihelion, P for close, doesn't make any sense. It's just you don't get that trick. It'll be high speed, high gravity. Gravity is dependent on the mass and distance between two objects. So if you make something more massive, if I were to grow in mass, gain mass, I'm more gravitationally attracted to the planets. Therefore, if you put a scale in between me and the planet, you're going to say way more, right? It's really because I'm more massive, and the laws of physics determine that I'm going to be yanked down harder by things. Everything in the universe is gravitationally attracted. I'm gravitationally attracted to this computer monitor right here. I'm not massive enough. That's not massive enough to really have that result in a force. It's not like things come flying at you. But something massive like a planet, certainly you feel the force of gravity with that, as does this monitor. It's being sucked towards this planet by the force of gravity. Go further away, if I took this monitor and threw it up into space, again, depending on its speed and trajectory and all of that, it can just go away, 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 because the further you get, the less the force of the gravity is. All right, so this guy, we nailed this a bunch. What I asked you to look for was, and I said there are two things. There's actually more than that. But what I asked you to look for are what two things might make this terrestrial group a thing and what might make this Jovian group a thing. There are questions that are going to happen here. So if you can get your cursor down there. Terrestrial. Sometimes known as the rocky planets. So what do we got? Well, first off, the easy one I think is that they're closer. They're the four closest. What else? If you come over here to diameter, we got a 4,000, a 12,000, 12,000, a 6,000. And then these 142, 120, 51, and 49. So these by far are the terrestrial ones are smaller. What else? Mass. Now, mass is like saying, okay, Earth is a mass of 1. The masses here are in Earths, which is a weird unit, but it works. You see the mass for all these are all lower. And density, 5.4, 5.2, 5.539 versus these that are in the ones, or that one's less than 1. That one would float in water technically. So higher density. All right. I know you're smart folks. You're going to say, well, you should do all the opposite here. It's true. Jovian, sometimes referred to as the gas giants, are the four furthest by distance, larger. Mass-wise, as we said, they are higher mass, but lower density. Now, if you go home and memorize these sentences, not really, because if you can just come in here and say T, J, there's 4 T's and 4 J's in that order, then this data table is sitting there for you. It's in the reference table. You can always use it. So this isn't really a memorized thing. It's more of a just the TJ is the only thing you really got to get down to be able to do that. Okay. This organization too, just on a side note, this is why kicking out Pluto was a good idea in my book and many people's books. once we kicked out Pluto, when I used to teach earth science back in, when did I start? 02 to 07 at my first job, Pluto was on this reference table. And it was always like, well, you got 4 terrestrial, you got 4 Jovian, here's all the properties, and then Pluto is this weirdo. Don't worry about it. So I think Pluto's more comfortable with its dwarf planet friends out there in the outer solar system, because that'd be the other side. If we said, okay, Pluto is a planet, well, then we'd have to bring a whole bunch of other like things that are like Pluto into the mix, and we'd be adding them all the time as we discover them. So I think it's a good idea that they said, that's it, 8 planets, then those other guys out there. All right, so yeah, check that reference table, use it. You're going to get some practice questions that will show you that sometimes they make you think a little bit and use these numbers, God forbid. But that really should be it. This is a decent way to pick some averages up. You know, there's not a ton of stuff on this test, and it's going to count more than the first test because it's more stuff. So some of you could really, well, everybody can make a pretty big swing on their grade right here, for better or for worse. So try to get these things down. See how it goes tomorrow. We'll see you then. Thanks for listening. Take care.